Hello and welcome back. We are going to extend our parser today to handle let expressions as well as identifiers. The identifiers obviously being the references to the bindings introduced by the lets. And last time we defined how the syntax tree is going to look like in this C data structure. So what I'm going to have is I'm going to have an array of bindings, and n gives us the number of bindings that we have. So these are the bindings, each binding being identifier equals expression, and then the body of the let expression, which is this thing. So for example, here there would be two bindings, one being a equals 1, the other one being b equals a plus 1, and this would be the body. And the binding looks very simple. It just has a name and it has the expression that's bound. So the name here would be a, and the expression here would be an integer expression of 1. And what we have to do now is we're going to have to extend parts expression to actually do that. So let's go to, let's go here to our parser. So the first case is here, expression being an identifier. This is very simple, because all I have to do is I have to token. I have to recognize that there's an identifier, and I already have the identifier, which is, and the name is in token.v. I don't remember. It's going to be in scanner. No, it's going to be compiler.h. So let's look at our token data structure again. Name. There we go. t.v.name. So that's the name. And I'm just going to expr equals alloc expr. And the expression that I need is probably expr ident. Expr ident. Now all I need to do is say expr v dot ident equals the name of the identifier in the token. And that's it. That's the identifier. Now the let, actually I should put the comments in here too. And this is the integer. Although it's not. That makes sense. Okay. So now this is going to be the more difficult one. And the reason this is a little bit more difficult is that this is the first case where we see a sequence. So these bindings can be any number of binding separated by end. It's not super difficult. We don't even need a look ahead yet, because after a binding, we either get an end, or if the list of bindings is finished, we get an in. Right? So basically, all we need to do is we read a binding, which is an identifier and equals, or an assignment operator and an expression, and then we look and we get a token and we say, are you an end? In which case we read another binding, or are you an in? Done with the bindings. So let's see, everything is a little bit more complicated, because we don't even have the super simplest data structures like, I don't know, an array that can grow dynamically. So we're going to have to implement that later on our own. But for now, I just want to I just want to focus on the parsing, and then afterwards we'll build the data structure. So we got the let. There's no information in the let. We need to have a loop here, and I don't know yet what the loop will have to look like. So I'll just put in an endless loop. This is how you write an endless loop in C, or like also write while true or something, but it's just the way it is. So what I'm reading is I'm reading the bindings, right? Which means I'm reading a binding first. Which means I need to read an integer. We do have an expect. Do we have an expect token? Does expect token actually return the token? No, it does not, but I'm going to make it return the token. Because I'm expecting an identifier, but I actually need its name. I can't just vanish into thin air. So I'm going to say t equals expect token context token ident. So now I have the name of the binding, right? So like the A, for example. Now I'm going to expect a token assign. So that's this token. Okay. And now I'm reading an expression. I'm going to call it whatever. I'm not even going to save it right now. Parse expr from the context. Actually, let's save it. Expr equals, and then later we'll figure out how to put it into a data structure. And now the moment of truth, where we have to scan a token which will be either an end or an in. Right, I'm going to say t equals, what is it called? Scan token, scan, t scan from context. Scan from context. And now this, I'm going to assert t dot type, yes, t dot type is either token end or t dot type equals token in. And now really all I need to do is, now I know what kind of a loop I want. Namely, I want to do while loop. And it's going to be while t dot type equals token in, end, I'm sorry. There's an end. We're still parsing more bindings. So if we've scanned the end, we're back to parsing in. So scan the end, we're parsing back to another identifier, another assignment, another expression. And if it's an in, then we're done, except that we need to parse the body, and then we need to parse the end. So expr equals parse expr context. That's the body. And then expect token end. And then we're done. So the parsing part should theoretically already work, except that we're not producing the correct syntax tree because we're ignoring most of it. But we can check that it actually does not crash. Yes. Do that by using parse main. So let's see if it compiles. It might not even compile, of course. It does. So now we have in tests parser 1.6, we have let.sl. So if I cat that, so this is exactly the test case from the assignment. So this should work. Well, what's going to work is the parsing should not crash. The output that we get should be wrong, because what will actually be returned is this expr, which is just the body. And then it's going to crash when we try to print the identifier. So let's actually fix that first. So if it is expr ident, then we are going to print the, do we just print the string? Yes, we just print the string. We just print string, which is expr v dot break. And then we have to implement case expr. Let's just do it. Let's just implement the let too. Why not? Printf let. And now the let is special in that the bindings get one additional level of indentation. So these are indented twice, and then the body is only indented once. So what I'm going to do is, now I need to, obviously iterate over expr v dot let dot n. It's 0, as long as it's less than that I++. And now I have the binding, which is expr v dot let dot. Let's go over to compiler.h. Let dot bindings of I, and that has a name and an expr. So what I need to do is, first of all, I need to print more indentation. So I'm gonna print indent, indent. I'm just factoring this thing out. So here, print indent, indent. What I'm doing here is I need to print 2 more indentations. I need to say printf. I'm printing the name first. Name. Actually, let me do binding t binding equals that. Name first, print indent plus 2, and then with an indent plus 3, print expr binding expr 15 plus 3. I've printed the name with an indentation of 2 relative this with an indentation of 3, and now I'm back to indentation plus 1, which prints the body. All of these, and then I'm doing print expr expr v dot let dot body with indent plus 1, and that should be that. Good. Let's see what happens if we simplang feed it this thing. Again, it should just print the body, right? So it should just print A plus B. And that's what it does, plus AB. So the idents work. Now we just need to get these into the bindings array. So I'm just going to invent an API, and then we're going to implement the API, because we need some kind of dynamic array that will collect these names and expressions for the bindings. So I'm going to call it dinrt r. Do I want to write an yes, I'm going to have to do dinr init array. So I'm initializing the array. And now what I'm going to do is I have here binding t binding L. Well, that's stupid. So the problem is that the array is not an array of pointers, it's an array of binding T's, right? But I don't wanna, I just wanna write a generic array of pointers. So I'm gonna do it really stupidly by allocating each of these dynamically. How do I allocate again? Pool, alloc, context pool, and then the size of. I'm gonna do pool, alloc, context, pool, except that to do this, size of binding T. Right, so now I have a binding, and I can put binding name equals T dot, what is it again? T dot ident, so that's the name. And here I'm just going to say binding expert. Now I have the binding. I'm going to say bind R append the array, the pointer. Now I have the pointer array. Now the problem is that expra equals alloc expra let, and this is actually the v.let.body. And that's the end, that's fine. And here I'm gonna move the whole thing over. And so the problem here is that I need to copy them. I need to copy not the pointers, but the contents of the bindings over. And actually what I need to do first is binding T bindings. I need to allocate the whole array. Size of binding T times, I'm going to call it length of my array. And now I need to do I have an I? No, I don't have an I. For int I equals 0, as long as I is less of din R length plus. I need to mem copy, which basically means copy by byte. Of course, it's more efficient than that, but in theory, you can. It just copies the contents of the memory. I'm copying 2 bindings of I from, bindings from R nth in R nth R I. So that's the nth pointer, or the ith pointer actually. And what I'm copying is binding, size of binding of T. And then all I need to do is expra v.let.n equals din R length of R, and expra v.let.bindings equals bindings. And that was super easy. And now all we need to do is implement these functions, and I'm gonna in r.h, and now all the standard C stuff, def in RH, find in R. This is why you don't want to program in C. So these are functions. We have dinar init, we have dinar append, we have dinar length, and we have dinar nth. And we also need to define our data structure, which is going to be the following. It's going to have a, well, actually, because I'm using dynamic allocation, because I'm allocating everything from the pools, I need to include pools.h, and it actually needs a pool. That's where it will allocate the dynamic array from. So we have the number of elements in there, but we're also allocating more than that so that we don't have to. It's basically just one array that if we fill it up, we allocate an array that's twice as big. So the capacity is how many elements fit into the array that we have allocated, and length is how many have we actually fit in there yet. And then we have the actual array. So this now actually, the init has to also get the context pool. And so this is a void bin array init, and it takes a pointer to an array and a pointer to a pool. The append takes a pointer to an array, and it takes a, how did I do that? That is weird. Interesting. I just pressed some key that made the doc go away. And a pointer, that's the pointer that we're appending. This I can actually implement, both of these I can implement in line. So I'm gonna put assert. This should actually be a size t. And it's an array. And it's going to be a static inline size t, and what it's going to do is it's going to return our length. So that's easy. So this actually, both of these should be size t's if we are proper. So if we are proper, then actually these should, whatever, I don't want to be that proper. And this is a static inline void star array, and it takes this and it takes size ti. And now what I have to assert first, assert is that the I is less than the length of the array. So let's say the array length is 5, then indexes 0 to 4 are valid. 5 is not valid because we start counting 0. And then I return our data of I. Now all I need to do is implement these two in r.c. Yes. Include in r.h. We almost got it. We're almost there. So we initialize the pool with the pool. We initialize the length with 0. I'm going to start with 8. Capacity equals 8. Let's start with 4. Most expensive 4. And now what I need to do is I need to allocate our data, which I'm going to pool alloc for from the pool, and it's size of pointer to void times our capacity. Right. Now in our append, what I need to do is if the length of the array is already at capacity, it should never be larger. So technically this should suffice, but for some reason I have this idea that I'm programming defensively if I write larger or equals. So if the length is, if I'm already at capacity, then what I need to do is I need to say I'm gonna increase the capacity by 2. And I'm gonna need to allocate from the pool, well, not yet. Not yet. Yeah. Allocate the new data array, but now I need to copy over to the new data the old data. And how many do I have to move over? Size of void star times our length. That's how many we have. And now I can say our data equals new data. And now all I need to do is say r of data of our length plus equals p. And that should work. So let's extend our makefile headers in r.h. Let's put it after the string in r.c. Let's see if that works. Okay, pool. Did you mean A to L? No, I did not. Oh, of course, it's from the array. Memcopy, yes. Memcopy for some reason is in string.h. Sub undeclared identifier. Yes, because I need to include it. Yes, good. No member t.v.ident. Really? Can we open? Oh, it's name. No member named ident. Oh, here too. Yes. Hooray. Okay, so what happens? And there we go. That's it. That should let's make sure that it is actually right for the same as well. I need to tell it first. Parts 1.6. The directory I'm testing, and it's versus simplang. I only put this one test file in there. 1 test, 0 failures. Hooray. So yeah, there we go. We have implemented the parser for let, and it seems to work. And of course, I could, you know, I should put in a test case where there's many. Let's do that, so that we at least test the array thing. Tests 1.6. It's called let many.sl. Yes. Now let's put in let a1 equals 1 and a2 equals 2 and 3, 4, 5, 6, 7, 8, 9, 10. Let's do that. And 2, 3, 4, 5, 6, 7, and in. I don't want to write an expression that's parenthesized with all of that. So I'm just going to return. Yeah, I should, whatever. I'm just interested in the parser anyway for now. So what I'm going to do is just return A1 plus A10, whatever. So that's what happens. Let's go. And there we go. Even that seems to work. A1 is 1, A2 is 2, A3 is 3, 4, 4, 5, 5, 6, 6, 7, 8, and this is plus A1, A10. So this looks correct. So I'm just going to put it into tests parser 1.6 let many.out. So now we have 2 test cases. All right. What are we doing next week? Next week, we are extending the interpreter to handle let. So what that means is that we will have to figure out a way to save the values of these assigned names, these variables, and then look them up later to do something like this. And that is made more difficult by the fact that names do not have to be unique, like here. So for example, this A is this A, but this A is a new A that's this A. But this A here is actually this A from outside. And we will figure all that out next week. Thank you so much. And goodbye.